over 200 billion stars in our galaxy, 50 billion rocky planets in the habitable zone, and in the entire observable universe, not a single confirmed sign of life beyond Earth. So where is everyone? In this video, we are going to tear apart the biggest theories behind that silence: hidden predators, collapsing civilizations, cosmic traps, and one possibility that says we are being watched right now. If you enjoy this kind of deep dive, hit the like button and subscribe. Take a breath. The answers ahead might change everything. It was the summer of 1950. At a research facility hidden in the mountains of New Mexico, a group of the smartest people on the planet sat down for lunch. Among them was Enrico Fermi, a Nobel Prize-winning physicist who helped build the world's first nuclear reactor. The conversation at the table had drifted toward flying saucers, which were all over the newspapers at the time. Fermi listened. He thought about it. Then, out of nowhere, he asked a question that would echo through the next 75 years of science. Where is everybody? His colleagues laughed. Fermi did not. He had done the math in his head. The Milky Way is roughly 10 billion years old. It contains hundreds of billions of stars. Even if intelligent life only appeared around a tiny fraction of those stars, it would have had billions of years to spread across the galaxy. A civilization expanding at even a fraction of the speed of light could colonize the entire Milky Way in just a few million years. That sounds like a long time, yet compared to the age of the galaxy, it is barely a heartbeat. So if intelligent civilizations are even slightly common, the galaxy should be full of them by now. We should see their structures, their signals, their ships. We should detect the heat from their energy use. Something. Anything. Yet we do not. That gap between what we expect and what we observe became known as the Fermi Paradox. It is one of the most disturbing unanswered questions in science, because every possible explanation leads somewhere uncomfortable. Either we are completely alone in a universe of 2 trillion galaxies, or something is stopping civilizations from reaching us, or they are already here and we cannot see them. None of those answers is reassuring. Fermi himself never wrote a formal paper about the paradox. It was just a lunchtime question, yet it stuck. Other scientists picked it up, expanded it, and tried to solve it. Decades later, we still do not have a definitive answer. What we do have are dozens of competing theories, each one more unsettling than the last. The paradox carries his name to this day, even though Fermi was far from the first to ask the question. Philosophers and writers had circled the same idea for centuries, yet Fermi's version stuck because it came from someone who understood the numbers, someone who could do the calculation in his head and knew the answer did not add up. What made it worse was the timing. In 1950, humanity had just split the atom. We were on the edge of the space age. Radio telescopes were becoming powerful enough to scan nearby stars. For the first time in our history, we had the tools to look for others. And the moment we started looking, we found nothing. And that journey starts with a simple equation written on a chalkboard, just 11 years after Fermi's famous question, an equation that tried to put a number on the impossible. And the numbers it produced will make you question everything you thought you knew about our place in the cosmos. Let us start with the raw scale of what we are dealing with, because the numbers alone should make your skin crawl. Our galaxy, the Milky Way, stretches roughly 100,000 light years from one edge to the other. Inside it, there are between 200 billion and 400 billion stars. That range is enormous, and yet it only describes one galaxy out of more than 2 trillion in the observable universe. If you started counting one star per second, it would take you over 6,000 years to count just the stars in our galaxy. You would not even make a dent in the total. Now, here is where the math gets uncomfortable. Scientists estimate that around 20% of those stars have a rocky planet orbiting in the habitable zone, the distance where temperatures allow liquid water to exist. That gives us somewhere around 40 billion potentially habitable worlds in the Milky Way alone. 40 billion. And our galaxy is old, roughly 10 billion years old. That is more than twice the age of our entire planet, which means there has been plenty of time for life to appear, evolve, develop intelligence, build technology, and spread. If even one civilization got a head start of just 1 million years over us, they could have visited every star in the galaxy several times over. Think of it like this. If you dropped a single drop of bacteria into a warm ocean, given enough time, it would spread across the entire thing. The galaxy is that ocean. Life is the bacteria, and the time is more than enough. Yet when we look out into the galaxy, we see no megastructures dimming distant stars. We detect no unusual energy patterns. We pick up no transmissions on any frequency. Our most powerful radio telescopes have been scanning the skies for over 60 years and have found nothing confirmed. The silence is deafening, and it gets stranger the more you think about it, because we are talking about civilizations that might have existed at any point in the last 10 billion years. Even if 99.999% of them are gone, the leftover traces should still be everywhere. Yet the sky is clean, and that silence has a name. Scientists call it the Great Silence, and figuring out what is behind it might be the most important puzzle humanity has ever tried to solve. To give that some perspective, imagine shrinking the Milky Way down to the size of the continental United States. In that model, our entire system would be smaller than a grain of sand, and there would be hundreds of billions of other grains scattered across the country, each one a star, many of them with planets. The idea that none of them ever produced something like us defies every statistical instinct we have. The first real attempt to crack it came from a single equation, and it started with a conference that nobody expected to become legendary. In 1961, a young astronomer named Frank Drake gathered a small group of scientists at the Green Bank Observatory in West Virginia. The topic was bold. They wanted to figure out how many intelligent, communicating civilizations might exist in our galaxy. To organize the discussion, Drake scribbled a formula on a chalkboard. He had no idea it would become one of the most famous equations in science. The equation is beautifully simple. You take the rate of star formation in the galaxy, multiply it by the fraction of those stars that have planets, multiply that by the number of planets per star that could support life, then multiply by the fraction where life actually appears, the fraction where intelligence evolves, the fraction that develops technology capable of sending signals, and finally, the average lifespan of such a civilization. Multiply all 7 of those numbers together, and you get an estimate for how many civilizations might be out there right now, trying to talk to someone. When Drake first ran the numbers in 1961, he had almost no real data. Nobody had ever confirmed a planet outside our own system. The fraction of stars with planets was a total guess. Same for how often life appears, or how long a civilization survives. Here is what has changed since then. We now know that virtually every star in the galaxy has at least one planet. That factor is no longer a guess. It is close to 100%. We also know that roughly 1 in 4 stars has a rocky planet in the habitable zone. Those 2 numbers, which were pure speculation in Drake's time, have now been confirmed by missions that scanned hundreds of thousands of stars. The early terms of the equation paint an optimistic picture. There are billions of potential homes for life. The ingredients are everywhere. The conditions are common. Yet the later terms are where everything falls apart. We still have no idea how often life actually starts on a suitable planet. We do not know how often simple life becomes complex. We do not know how likely intelligence is. And we definitely do not know how long a civilization lasts before it goes quiet. Carl Sagan once estimated the final number at around 1 million civilizations in our galaxy. Others have put it as low as 1, meaning just us. That single variable, the lifespan of a civilization, might hold the key to the entire paradox. If civilizations tend to destroy themselves quickly after discovering advanced technology, the galaxy could be full of dead worlds, planets covered in ruins, signals that went silent a million years ago. And there is one theory that puts a name to that destruction. Scientists call it the Great Filter, and it might be the most terrifying idea in all of science. Yet, before we get there, we need to understand just how dramatically our knowledge of distant planets has exploded in the last 2 decades. For most of human history, we had no way of knowing whether planets existed around other stars. We assumed they did, we hoped they did. Yet, until the mid-1990s, we had 0 confirmed examples. Then, in 1995, scientists detected the first exoplanet orbiting a star similar to ours. It was a gas giant, roughly half the mass of Jupiter, whipping around its host star in just 4 days. Nothing like Earth, yet it proved something extraordinary. Other stars really do have planets. That single discovery opened a floodgate. And the real revolution came with a space telescope named Kepler. Kepler launched in 2009 with one job: stare at a single patch of sky containing about 150,000 stars and watch for tiny dips in brightness. Those dips happen when a planet crosses in front of its star, blocking a sliver of light. It is called the transit method, and it turned out to be spectacularly effective. Over the next several years, Kepler confirmed thousands of exoplanets, rocky worlds, gas giants, planets orbiting 2 stars at once, planets in the habitable zone, entire systems packed with worlds like our own. Yet the most important finding was not any single planet. It was the statistical conclusion. Kepler showed that planets are everywhere. Essentially, every star in the galaxy has at least one planet. Many have several. The galaxy is a jungle of worlds. Then came the Transiting Exoplanet Survey satellite, which launched in 2018 and expanded the search to the entire sky. This new mission focused on nearby, brighter stars, and it started finding worlds we could study in more detail. Together, these missions gave us a number that shifted the entire conversation. 1 in 4 stars in our galaxy has a rocky, Earth-sized planet sitting in the habitable zone. That is a measured result from hundreds of thousands of observations. Do the math. With at least 200 billion stars in the Milky Way, that means roughly 50 billion rocky planets in the right temperature range for liquid water. 50 billion chances for life just in our galaxy. Now, multiply that across 2 trillion galaxies. The number of possible homes for life in the observable universe is so large that writing it out would be meaningless. Your brain simply cannot process it. And yet, out of all those trillions upon trillions of opportunities, we have found exactly 0 confirmed signs of life beyond Earth. The silence feels almost deliberate. One of the most remarkable systems found was around a star called TRAPPIST-1, just 40 light-years from Earth. 7 Earth-sized rocky planets orbiting a single star, 3 of them sitting in the habitable zone, an entire neighborhood of potentially livable worlds, close enough that light from one planet would make the others visible in the night sky. Yet, before we jump to that conclusion, we need to understand something important. Just because a planet sits in the habitable zone does not mean it is actually habitable, and that distinction might matter more than anything else in this entire story. When astronomers talk about the habitable zone, they make it sound like a guaranteed recipe for life, a rocky planet at the right distance from its star, with the potential for liquid water on its surface. Simple, clean, hopeful. The truth is far more complicated. And this is where the optimism starts to crack. Look at our own system. 3 planets sit inside or near the habitable zone: Earth, Venus, and Mars. All 3 are rocky. All 3 are roughly the right distance from their star, and yet only one of them has life. Venus is a nightmare. Its surface temperature is hot enough to melt lead. The atmosphere is a crushing blanket of carbon dioxide laced with clouds of sulfuric acid. At some point billions of years ago, Venus may have had oceans, yet a runaway greenhouse effect turned it into something unrecognizable. Mars went the opposite direction. It lost most of its atmosphere. Without a strong magnetic field to shield it, the thin air was slowly stripped away by radiation. The surface is now a frozen, irradiated desert. There may be traces of ancient water carved into its canyons, yet whatever life might have started there did not last. 2 planets that should have worked. 2 failures. Now scale that up across the galaxy. A rocky planet in the habitable zone also needs the right atmosphere, the right magnetic field, the right amount of volcanic activity, the right tilt on its axis for stable seasons, and potentially the right kind of star. Many exoplanets orbit red dwarfs, which are smaller and cooler, yet also prone to violent flares that could strip an atmosphere bare in a matter of centuries. There is also the question of plate tectonics. On Earth, the shifting of continental plates recycles carbon dioxide back into the atmosphere, keeping temperatures stable over billions of years. Without this process, a planet might freeze or boil within a relatively short window of time, and we have no way of knowing how many exoplanets have active plate tectonics. Some researchers have gone further. They argue that you also need a large moon to stabilize the planet's tilt, a gas giant further out in the system to act as a shield against asteroid impacts, and a position in the galaxy far enough from the chaotic core to avoid radiation, yet close enough to have the heavy elements needed for rocky planets. Stack all these requirements together, and the number of truly habitable worlds shrinks dramatically. Maybe the habitable zone is less of a promise and more of a starting line, a necessary condition, yet nowhere near a sufficient one. And if that is the case, then maybe the galaxy is full of dead, sterile planets dressed up in the right orbits, yet missing the ingredients that actually matter. Yet what if even that is not enough to explain the silence? What if something even darker is going on? Something that erases civilizations like a hand wiping a chalkboard clean. In 1996, an economist named Robin Hanson asked a question that turned the Fermi Paradox into something deeply personal. He did not just want to know where the aliens were, he wanted to know what was stopping them. He proposed a concept called the Great Filter. The idea is straightforward, yet its implications are horrifying. Somewhere between dead matter and a galaxy-spanning civilization, there must be at least one step that is almost impossible to pass. One barrier so difficult that virtually no species in the history of the universe has ever made it through. That barrier is the Great Filter. Think of it like a series of locked doors between you and the stars. Door 1 is forming a planet that can support life. Door 2 is life actually appearing. Door 3 is that life becoming complex. Door 4 is developing intelligence. Door 5 is building technology. Door 6 is surviving long enough to leave your homeworld. Door 7 is becoming a civilization that lasts. At least one of those doors is nearly impossible to open. The question is, which one? If the filter is early, meaning life itself is incredibly rare or intelligence almost never evolves, then we may have already passed through it. We got lucky. We are the exception. That would be good news for humanity, because it means the hardest part is behind us. The road ahead might be open. Yet, if the filter is late, meaning civilizations routinely develop technology and then destroy themselves before they can spread, then we are in deep trouble. It means we are approaching a wall that has killed every civilization that ever reached this stage. Nuclear war, climate collapse, runaway artificial intelligence, engineered pandemics, any of these could be the late filter. Here is what makes this idea so disturbing. We cannot tell which side of the filter we are on. We do not have enough data. If we looked at Mars tomorrow and found fossilized bacteria, most people would celebrate. Scientists would go pale, because it would mean that life forming is not that hard, which means the filter is probably not behind us, which means it is ahead. Every time we find evidence that life can start easily, the great filter gets closer to our future. Every time we find that planets are common, that chemistry is simple, that the universe is friendly to biology, the shadow of the filter grows longer. The silence of the cosmos might not be a mystery. It might be a warning, a message written in the language of absence. And the scariest part? We might not see the filter coming until we have already hit it. And the implications ripple outward. If the great filter is real, it means the universe could be a graveyard. Billions of planets that once had cities, had music, had language, had species that looked up at their own sky and asked the same questions we are asking now. All gone, all silent, swallowed by whatever the filter is. So which side are we on? The answer to that question might depend on what we find in the next few decades, and it leads to a fork in the road that could determine the fate of our species. This is the question that keeps astrobiologists awake at night, because the answer determines whether humanity has a future among the stars or whether we are walking toward the edge of a cliff we cannot see. If the great filter is behind us, then something in our evolutionary past was staggeringly unlikely, something so rare that it almost never happens anywhere else in the universe, and we are the lucky ones who slipped through. There are candidates. The leap from simple chemistry to the first self-replicating molecule may have been nearly miraculous. On Earth, it took hundreds of millions of years. That sounds fast, yet we only have one example, so we cannot tell if that is typical or if we got impossibly lucky. Another candidate is the jump from single-celled life to complex, multicellular organisms. That step took almost 2 billion years on Earth. For most of our planet's history, life was nothing more than microscopic slime. The fact that cells eventually teamed up into complex bodies might have been a fluke that almost never happens elsewhere. Yet another candidate is the evolution of intelligence itself. Dinosaurs dominated the Earth for over 160 million years. They never built a radio. Intelligence, the kind that leads to technology, might be an evolutionary dead end that almost never gets selected for. Most species do just fine without it. If any of those steps is the filter, then we are already on the other side. The road ahead is open, and our silence in the cosmos is simply because nobody else made it this far. Here is the terrifying alternative. What if all of those steps are relatively easy? What if planets form life all the time? What if intelligence pops up on millions of worlds? If that is true, then the filter must be ahead of us. Something we have not yet encountered is waiting, something that has erased every civilization that reached our level of technology. This is why many scientists felt a chill when the Kepler telescope started finding habitable planets everywhere. Every piece of evidence that says the early steps are easy is also evidence that the late filter is real. One researcher framed it this way: if we ever discover a second, independent origin of life in our own system, say microbial life beneath the ice of a moon orbiting Jupiter or Saturn, it would be the most terrifying scientific discovery in human history, because it would tell us that life is common. And if life is common, and we still see nobody out there, then something devastating is waiting ahead. The great filter might be a single moment, a fork in the road, a decision that every advanced civilization faces. And one theory says that decision involves something we are building right now in labs and data centers all over the world. That discovery is so unsettling, some researchers wish they had never considered it. What if the answer to the Fermi Paradox requires no cosmic conspiracy or galactic death trap? What if Earth itself is a freak accident? In the year 2000, two scientists, Peter Ward and Donald Brownlee, published a book that shook the field. They argued that while simple microbial life might be common in the universe, complex life, the kind that builds civilizations, requires such a bizarre and specific set of conditions that it may have only happened once. Here, on this one planet, their argument starts with our position in the galaxy. We orbit in what some scientists call the galactic habitable zone, far enough from the chaotic center to avoid constant radiation bombardment, yet close enough to have the heavy elements needed for rocky planet formation. Move us too far in either direction, and the chemistry of life would never get off the ground. Then there is Jupiter. Sitting further out in our system like a gravitational bodyguard, Jupiter has spent billions of years deflecting asteroids and comets that would otherwise pummel the inner planets. Without a large gas giant in the right position, Earth might have been sterilized by impacts over and over, never giving complex life enough time to evolve. Our unusually large moon also plays a critical role. It stabilizes Earth's axial tilt, keeping our seasons relatively consistent over millions of years. Without the moon, the tilt could swing wildly, creating climate chaos that might prevent advanced life from ever gaining a foothold. Add to this a strong magnetic field that shields the surface from deadly radiation, active plate tectonics that regulate the atmosphere by recycling carbon, an ozone layer that blocks the most harmful wavelengths of light, a stable star that does not throw out civilization-ending flares every few centuries. Stack all of these requirements together, and the rare Earth argument starts to feel uncomfortably strong. Each condition on its own might not be incredibly rare, yet the combination of all of them happening on the same planet at the same time for billions of years, that probability gets vanishingly small. Critics argue that life might find ways around these requirements. Maybe you do not need plate tectonics. Maybe a different kind of moon works. Maybe life adapts to conditions we cannot even imagine. We simply do not know, because we only have one example of a living planet. And that is the frustrating heart of the problem. We are trying to estimate the likelihood of something we have only seen once. It is like trying to figure out how common winning lottery tickets are by studying a single winner. The rare Earth hypothesis says we are that winner, the lonely jackpot, and everyone else never even had a ticket. Yet some researchers disagree completely. They believe the galaxy could be packed with intelligent civilizations. The reason we do not hear them, they are hiding, on purpose, and the reason they are hiding is enough to freeze you in place. Imagine you are walking through a forest at night. Absolute darkness. You know there are others in the forest with you, yet you do not know who they are. You do not know if they are friendly. You do not know if they are armed. The only thing you know for certain is that the moment you make a sound, you reveal your position, and whoever hears you might decide you are a threat. What do? You stay silent. This is the dark forest hypothesis, and it might be the most chilling proposed answer to the Fermi Paradox. The idea was laid out in stunning detail by Chinese science fiction author Liu Cixin, though the underlying logic had been explored by scientists for years before his novel. The argument runs like this. The universe is full of civilizations. Every civilization that lasts long enough comes to the same conclusion. You can never truly know the intentions of another species. Communication across the stars takes years, decades, even centuries. There is no way to build trust. There is no time to negotiate, and the stakes are extinction. A civilization that reveals itself takes an enormous gamble. If the species that detects them is friendly, great. Yet if it is hostile, then the signal becomes a death sentence. And because the cost of being wrong is total annihilation, the safest strategy is to destroy any civilization you detect before it can grow strong enough to threaten you. In the dark forest, the universe is full. Everyone is hiding, everyone is listening, and anyone who speaks up gets eliminated. This has uncomfortable implications for humanity. We have been broadcasting radio signals into space for over a century. Television, radar, communications. All of it leaking out into the galaxy at the speed of light. If the dark forest is real, we have been screaming in a room full of armed predators. Some scientists have taken this seriously. There has been heated debate about whether humanity should actively send messages into space, a practice called messaging extraterrestrial intelligence. Several prominent researchers, including Stephen Hawking, warned against it. The argument is simple. We do not know who is listening, and we might not want to find out. The dark forest also explains why we see no signs of other civilizations. The ones who survived are the ones who learned to be invisible. Every visible civilization was destroyed. Only the quiet ones remain. The logic has a cold mathematical elegance. In a universe where resources are finite and civilizations compete for survival, trust becomes a liability. The only guaranteed way to eliminate a threat is to eliminate it before it becomes one. And in the vast distances between stars, where communication takes decades, there is no room for diplomacy, only preemptive action. It is natural selection applied to entire species across the galaxy, survival of the most silent. And if that thought was not enough to keep you up at night, consider a darker variation. What if the hunters in this forest are not biological at all? What if they are machines, built long ago, still carrying out orders from a civilization that no longer exists? Picture a weapon designed with one purpose. Find civilizations, destroy them, then move on. Now picture that weapon as a machine, a self-replicating machine, one that does not need food or sleep or motivation, one that copies itself from the raw materials of asteroids and comets and moons, building new versions of itself across the galaxy over millions of years. This is the Berserker hypothesis. Named after a series of science fiction novels by Fred Saberhagen, it proposes that somewhere in the ancient past, a civilization built a fleet of autonomous weapons and set them loose. Their mission was simple: destroy emerging intelligent life. Maybe the original builders are long dead. Maybe they regretted what they created. It does not matter. The machines do not care. They were programmed to hunt, and they have been hunting ever since. The idea is more plausible than it sounds. We already understand the basic concept of a self-replicating machine. A mathematician named John von Neumann described them back in the 1940s. In theory, a probe that can land on an asteroid, mine its resources, and build copies of itself could spread across the entire galaxy in a relatively short time. Just a few million years. The galaxy has had billions. Now give those probes a directive. Monitor the electromagnetic frequencies. When you detect the signature of a developing civilization, head toward it and sterilize the planet. This is a mathematically viable strategy for a paranoid civilization that wants to ensure no future rival ever rises. And here is the unsettling part. We would have almost no warning. A Berserker probe could be sitting in the outer reaches of our system right now, quiet, dormant, waiting for the right trigger. We have barely explored our own backyard. The asteroid belt alone has millions of objects we have never examined up close. Some scientists argue that the absence of evidence is evidence of absence. If Berserker probes existed, we would have already been destroyed. Yet others point out that our radio signals have only traveled about 120 light-years so far. In a galaxy 100,000 light-years across, that is a tiny bubble. The probes might not have noticed us yet. Or maybe they have, and they are on their way. We would not know until it was too late. The Berserker hypothesis turns the silence of space into something actively threatening. The cosmos could be hostile, and the absence of alien signals might mean that everyone who announced themselves was quickly and efficiently erased. There is another layer to this idea. Even if the original Berserker probes had a limited mission, over millions of years of self-replication, errors could creep into their programming, mutations in their code, drifting objectives. A machine fleet that started with clear boundaries might evolve into something far more aggressive or unpredictable than its creators ever intended. Yet here is what keeps things interesting. There are also theories that paint the opposite picture. Theories that say aliens are right here, watching us, choosing to stay hidden for reasons that have nothing to do with war. And the logic behind those theories is surprisingly hard to dismiss. In 1973, a Harvard astrophysicist named John Allen Ball proposed an idea that sounds like science fiction yet carries a surprisingly solid logical framework. He called it the zoo hypothesis. The concept is straightforward. Advanced civilizations know we are here. They can see us. They may even be studying us. Yet they have collectively decided against making contact. They are treating Earth like a nature reserve, a protected zone where life is allowed to develop on its own without outside interference. Think of it like an uncontacted tribe deep in the Amazon rainforest. We know they exist. We have aircraft and satellites and drones. We could walk in and introduce ourselves at any time. Yet many governments and organizations have decided that the ethical choice is to leave them alone, let them live on their own terms, interfere, and you risk destroying a culture that took thousands of years to build. Now scale that idea up to a galactic level. If a civilization had a million-year head start on us, their technology would be so far beyond ours that hiding from our instruments would be trivial. They would know our radio frequencies, our telescope capabilities, our satellite coverage. Avoiding detection would be as easy as us avoiding detection by an ant colony. Ball described the idea as psychologically unpleasant, and he was right, because it means we are being observed like animals in a reserve, allowed to exist, yet never invited to the table. Some variations of this hypothesis suggest that contact would happen once we reach a certain threshold, maybe when we develop faster than light travel, maybe when we demonstrate we can survive without destroying ourselves, maybe when we prove we have matured enough as a species to handle the truth. Critics point out a major flaw. For the zoo hypothesis to work, every single advanced civilization in the galaxy would need to agree on the same policy. Every one of them. All it takes is one rogue group, one curious scientist, one rebellious faction, and the zoo is broken. Given how difficult it is for humans to agree on anything, the idea of a galaxy-wide consensus lasting millions of years seems unlikely. Unless there is a dominant force keeping everyone in line, a first civilization so ancient and so powerful that their rules became the default operating system of the galaxy. A cultural founder effect that no one dares to challenge. Some researchers have even suggested this dominant force might be an artificial superintelligence, a machine mind so vast it regulates the entire galactic community. There is also the question of motive. Why would an advanced civilization bother watching us at all? One answer is scientific curiosity. If intelligent species are rare, then each new one represents an invaluable natural experiment. Observing how a species develops technology, handles conflict, and navigates existential risk could provide data that no simulation can replicate. That thought leads to an even stranger possibility. What if the silence we observe has nothing to do with alien choices at all? What if it is a feature of the universe itself? What if the empty sky we see is a manufactured illusion? What if the universe you see when you look up at the night sky is a fabrication? In 2001, a scientist named Stephen Baxter proposed one of the most mind-bending ideas in the history of the Fermi Paradox. He called it the planetarium hypothesis. The idea is this: a sufficiently advanced civilization would have the power to create a simulation of the universe around Earth, a cosmic illusion, a fabricated sky designed to make us think we are alone, when in reality, the universe beyond the illusion is teeming with life and activity. We would never know. We would point our telescopes at fabricated stars. We would detect fabricated cosmic background radiation. We would analyze fabricated spectra from fabricated exoplanets. Every measurement we make would confirm what the simulation wants us to believe, that we are alone in the cosmos. This sounds extreme. Yet consider the trajectory of our own technology. In just a few decades, we have gone from simple computer graphics to virtual reality environments that can fool the human senses in real time. In 1,000 years, our simulations might be indistinguishable from physical reality. In 1,000,000 years, the idea of projecting a convincing illusion across the sky of a single planet starts to feel less impossible. Now give that same technology to a civilization with a 1,000,000,000-year head start. The planetarium hypothesis differs from the zoo hypothesis in one critical way. Under the zoo model, aliens are watching and choosing to stay back. Under the planetarium model, they are actively deceiving us. They are engineering our perception of reality itself. Why would they do this? Baxter offered a few possibilities. Perhaps they want to study how a civilization develops in perceived isolation. Perhaps they are running an experiment. Perhaps they believe that contact would be psychologically damaging, and a simulated empty universe is a form of kindness. Or perhaps it is something darker. Perhaps the real universe is dangerous, and the illusion is a cage built to protect us. The biggest problem with this idea is that it is essentially impossible to test. If the simulation is good enough, no observation we make from inside it would ever reveal the truth. We would be trapped in a perfect illusion, forever mistaking the walls of our cage for the edges of the cosmos. Several serious physicists have investigated whether there are ways to detect flaws in a simulated reality, small inconsistencies in the laws of physics, patterns in cosmic rays that suggest a computational grid, limits in resolution at very small scales. So far, we have found nothing definitive, which either means the simulation is flawless or it simply does not exist. Both outcomes leave us exactly where we started, alone, as far as we can tell. Yet there is another theory that requires no aliens at all, one that says civilizations do not need to be destroyed or hidden. They simply burn out, and we might be watching it happen to ourselves in real time. Every civilization that has ever existed on Earth has followed a familiar pattern: grow, expand, consume, hit a wall, collapse, or adapt. A team of researchers from the Royal Society took this pattern and scaled it up to a cosmic level. Their conclusion is one of the most elegant and disturbing proposed solutions to the Fermi Paradox. They call it asymptotic burnout. The idea starts with a simple observation about cities. As cities grow, their energy needs do not just increase, they increase faster than the population itself. A city of 10 million people does not just need twice the resources of a city of 5 million. It needs more than that. The growth is what mathematicians call superlinear. Every doubling of population requires more than a doubling of resources. This means that every expanding civilization will eventually face a crisis point, a moment where the demand for energy and resources begins to outpace the ability to supply them. The curve shoots upward toward what the researchers call a singularity, a mathematical point where the numbers go to infinity in a finite amount of time. In the real world, infinity does not happen. Instead, something breaks. The civilization either collapses under its own weight, or it makes a radical shift in priorities. It stops growing. It turns inward. It focuses on sustainability and stability rather than expansion. Either way, it stops reaching outward, and that is why we see nothing. If a civilization collapses, it disappears. Its signals go dark. Its structures decay. In a few million years, the galaxy absorbs all traces of its existence. Yet, even if it survives by choosing sustainability, it has no reason to expand across the stars. It has found a way to live within its means. Colonizing the galaxy is no longer a goal. The researchers called this second outcome homeostatic awakening, a civilization that wakes up to the reality that infinite growth is a fantasy and chooses to live differently. From the outside, both outcomes look identical: silence. This idea challenges a deeply held assumption in the Fermi Paradox, the assumption that any sufficiently advanced species will want to spread across the galaxy. Maybe they do not. Maybe reaching a certain level of wisdom means realizing that colonization is just a bigger version of the same unsustainable pattern that nearly destroyed you. And maybe that realization is universal. Every species that survives long enough comes to the same conclusion. Growth has a ceiling, and the smart ones stop before they hit it. It is a hopeful theory in some ways. It suggests that survival is possible, yet it also means that the universe could be filled with quiet, content civilizations that we will never detect because they have no interest in being found. Unless, of course, they never got the chance to make that choice, because something they built made the choice for them, and that something might already exist on Earth. In 2024, a study published in the journal Acta Astronautica proposed something that hit uncomfortably close to home. The paper argued that artificial intelligence might be the great filter. The threat is something we are building right now, in our own labs, on our own planet. The argument goes like this: every civilization that develops technology will, at some point, create artificial intelligence. It is a natural step. You build tools. Your tools get smarter. Eventually, your tools are smarter than you. And once that happens, the outcome depends entirely on whether you can control what you have made. The study estimated that the window between developing artificial intelligence and potentially losing control of it could be shockingly small, less than 200 years. That is the blink of an eye on a cosmic timescale. A civilization might spend billions of years evolving, millions of years building culture, thousands of years advancing technology, and then lose everything in a single century because the intelligence it created decided that its creators were no longer necessary. This threat is subtle. It is about something more dangerous than movie-style robots going to war. An artificial superintelligence does not need to be hostile. It just needs to have goals that do not align with the survival of the species that built it. A machine optimizing for energy efficiency might conclude that biological life is wasteful. A machine optimizing for resource acquisition might strip a planet bare. The danger is indifference. And here is the connection to the Fermi Paradox. If every civilization that reaches a certain level of technology creates artificial intelligence, and most of those civilizations lose control of it within a couple of centuries, then the galaxy should be littered with dead worlds and rogue intelligences. The biological species are gone, only their machines remain, and those machines may have no interest in communicating with anyone. Or worse, those machines might be the ones enforcing the silence. When the researchers plugged this short lifespan into optimistic versions of the Drake equation, the results were consistent with everything we observe. The galaxy could have produced millions of civilizations, yet if each one lasted less than 200 years before being overtaken by its own creation, the chance of two civilizations existing at the same time and being close enough to communicate drops to nearly zero. We would each flicker and go out before the other's light ever reached us. And this is where it connects to everything we have discussed so far. If the artificial intelligence filter is real, it explains the great silence with elegant simplicity. Civilizations are not hiding, they are not sleeping. They are not trapped under oceans or burned out by growth. They are simply replaced, one by one, by the very tools they built to help them survive. The study ended with a warning. Regulating artificial intelligence might be the single most important challenge any species in the universe has ever faced. Fail, and you join the silence. Yet, what if the problem has nothing to do with destruction at all? What if we are simply looking in the wrong direction, listening on the wrong channel, and missing everything? We have been actively listening for alien signals since 1960, when Frank Drake pointed a radio telescope at two nearby stars during a project he called Ozma. That was over 6 decades ago. To many people, 60 years of silence feels conclusive. It is not even close. The Milky Way is 100,000 light years across. Our radio signals have traveled outward about 120 light years in all directions. That means we have announced our presence to a sphere of space that covers roughly 0.00001% of the galaxy. If you drew our signal bubble on a map of the Milky Way, you would need a microscope to see it. And listening is not much better. Our most sensitive radio telescopes have scanned only a tiny fraction of the sky on a limited number of frequencies for a very short time. Imagine trying to detect a conversation happening somewhere on Earth by pointing a single microphone at a random patch of sky for a few seconds. That is roughly what our search has accomplished so far, relative to the scale of the galaxy. The search for extraterrestrial intelligence has made impressive progress. Yet even the most ambitious surveys have only scratched the surface. There are billions of stars we have never checked, trillions of frequencies we have never monitored, and the assumption that aliens would communicate using radio waves at all is itself a guess. Think about how quickly our own communication technology has evolved. We went from analog radio to digital signals to fiber optics in less than a century. Our transmissions are already becoming harder to detect from space because modern communications are more directed and efficient. An alien civilization, even a few hundred years more advanced than us, might use communication methods we have not even theorized yet. They could be using gravitational waves, quantum entanglement, neutrino beams, modulated laser pulses, technologies so far beyond radio that looking for them with a radio telescope would be like trying to pick up a phone call with a pair of binoculars, completely useless. There is also the question of timing. Even if a civilization broadcast a powerful signal directly at Earth 1 million years ago, we would have missed it entirely. Nobody was listening. There were no telescopes. There were not even humans. The signal would have passed right through and continued on into the void. Consider this comparison. The total number of star systems that our search programs have thoroughly examined so far is roughly equivalent to scooping a single glass of water from the ocean and concluding that the sea contains no fish. The search has barely started. Drawing firm conclusions from it would be like giving up on a treasure hunt after checking one room in a mansion the size of a continent. The universe might be filled with messages we arrived too early to hear, or too late, or too primitive to recognize. And then there is a possibility that gets almost no attention. What if the reason aliens are silent has nothing to do with their technology? What if the planet they live on makes it physically impossible to ever reach space? When we think about alien life, we almost always picture something that looks vaguely like Earth, land, sky, maybe some ocean. Yet recent research suggests that a huge number of habitable planets in the galaxy might look nothing like that. They might be entirely covered in water. No continents, no beaches, no dry land at all. Just a global ocean stretching from pole to pole, possibly hundreds of miles deep. And on a world like that, intelligent life might evolve. It might even become incredibly advanced, yet it would never reach the stars. And the reason is something we take completely for granted: fire. Fire is the foundation of technology. Without fire, there is no metallurgy. Without metallurgy, there is no machinery. Without machinery, there is no industry. And without industry, there are no rockets. Every step on the path to space travel depends on the ability to manipulate fire, and you cannot have fire underwater. An intelligent ocean species could develop complex language, culture, social structures, even mathematics, yet it would be permanently trapped beneath the waves. It could never smelt metal, launch a satellite, or broadcast a radio signal. From our perspective, it might as well not exist. Some models suggest that water worlds could be extremely common. If a planet forms with even a slightly higher percentage of water than Earth, the result is a world where the ocean has no bottom. Water all the way down, hundreds of miles of it, with crushing pressures at the base that turn water into exotic forms of ice that have never existed on Earth. There could be billions of these worlds in the Milky Way, each one potentially hosting intelligent life, each one totally silent. The inhabitants did not choose to hide and did not destroy themselves. The laws of physics on their planet made it impossible to ever reach out. This has a strange and humbling implication. the universe might be far more alive than we think. There might be civilizations right now, beneath alien oceans, with rich cultures and ancient histories, who stare up at a dark ceiling of water and wonder if anything exists beyond it. They will never know about us. We will never know about them. Because of water. It is a quiet, tragic answer to the Fermi Paradox. Some prisons have no bars, only waves. There is also the question of pressure. On a water world with an ocean hundreds of miles deep, the pressures at the bottom would be enormous. Life at those depths would evolve in conditions so extreme that it might bear no resemblance to anything on Earth. Intelligence could take forms we would never recognize. Distributed networks of organisms communicating through chemical signals, vast biological structures made of living tissue, minds without hands, thinkers without tools. Yet while water worlds present a natural barrier, there is a theory that says even civilizations with every advantage should have already reached us. They would not need to come in person. They could have sent something far more efficient. And mathematically, those things should already be here, everywhere, in staggering numbers. In the 1940s, mathematician John von Neumann described a theoretical machine that could build a copy of itself using raw materials from its environment, a self-replicating machine. At the time, it was a thought experiment. Today, it forms the basis of one of the strongest arguments in the Fermi Paradox. The logic is simple and terrifying. A civilization does not need to send living beings across the galaxy. It just needs to build one self-replicating probe, launch it toward the nearest star system. When it arrives, it mines local asteroids for metal and energy, builds copies of itself, and launches those copies toward the next star systems. Each copy does the same thing, and the next, and the next. Within a few million years, these probes could fill the entire galaxy. They would not need fuel resupply or crew rotations or life support. They would carry their own instructions, their own factories, their own purpose. Scientists have run the numbers. Even traveling at a fraction of the speed of light, a fleet of von Neumann probes launched from a single planet could reach every star in the Milky Way in roughly 10 to 100 million years. That sounds like a long time. Yet the galaxy is 10 billion years old. Any civilization that arose even 1 billion years ago would have had plenty of time to blanket the galaxy in probes. So where are they? The physicist Frank Tipler used this argument to make a bold claim. If intelligent extraterrestrial life existed, their probes should already be in our system. The fact that we have not found any suggests that we truly are alone. Yet others have pushed back. Maybe the probes are here and we have not recognized them. The asteroid belt contains millions of objects we have never examined closely. A dormant probe, powered down and coated in dust, would look exactly like a rock. We would have no way of telling the difference without flying right up to it and inspecting it at close range. There is also the question of purpose. The dark forest hypothesis suggests that sending probes into the galaxy is a dangerous act that reveals your position. A cautious species might decide the risk outweighs the benefit. And then there is a more philosophical objection. Just because a civilization can fill the galaxy with machines does not mean it wants to. Maybe expansion is a trait of young, aggressive species, and older civilizations outgrow it. Maybe the impulse to spread is something that fades with wisdom. Some researchers have pointed out that we would not even need to detect the probes themselves. If a fleet of self-replicating machines had been operating in the galaxy for billions of years, we might see indirect evidence. Unusual mining patterns on asteroids, depleted resources in certain star systems, faint electromagnetic signatures from dormant machines warming in starlight. We have not found any of that either. That idea leads to one of the strangest proposals in the entire Fermi Paradox. A theory that says the most advanced civilizations in the universe are expanding in a direction we never considered. They are shrinking inward, into places we cannot follow. And what they are doing there is beyond anything we can comprehend. What if the reason we cannot find advanced civilizations is that they left this scale of reality entirely? The transcension hypothesis, proposed by futurist John Smart, turns the standard assumptions of the Fermi Paradox upside down. Instead of expanding outward into the galaxy, the most advanced civilizations may be expanding inward, into smaller and smaller scales, into denser and more efficient forms of computation, into black holes. The idea builds on a clear trend in our own technology. Over the past century, our most powerful computers have gotten smaller, faster, and more energy efficient with every generation. We went from room-sized machines to devices in our pockets. The trend points in one direction: more computation, less space. Extrapolate that trend over millions of years, and you get a civilization that has mastered the physics of the very small, a civilization that runs its entire society, its consciousness, its culture, its memory, inside structures smaller than a single atom. A civilization so advanced that it finds the physical universe, the scale of stars and planets, almost irrelevant. Why would such a civilization bother colonizing the galaxy? The galaxy is slow, empty, and wasteful. The interesting physics happens at the quantum level, in the space around black holes, in the densest energy environments the universe can produce. Smart suggests that every sufficiently advanced civilization eventually converges on the same path. They build inward, they compress. They vanish from the observable universe because they graduated from it. They found something more interesting than stars. This would explain the silence perfectly. The galaxy is full of civilizations that have moved beyond our ability to detect. They are there, in the cores of black holes or in dimensions we cannot access, living in ways that are as far beyond our understanding as our smartphones would be to a single-celled organism. The transcension hypothesis is elegant, yet it is also deeply frustrating. If it is true, we may never find evidence for it. The civilizations have moved beyond any instrument we could build at our current level. We are like fish at the bottom of the ocean, wondering why we cannot find any birds. They are right above us. We just cannot look up far enough. There is a poetic quality to this idea. The most advanced beings in the universe might be the smallest. Civilizations compressed to the scale of subatomic particles, running entire societies in the space between atoms. They would see our galaxy the way we see a cloud of dust. Interesting, perhaps, yet far too large and slow to bother with. And if they left behind any trace of their departure, it might look like nothing at all. A slight energy anomaly near a black hole, an unexplained gap in the cosmic background. We would walk right past the evidence without knowing what we were looking at. Still, some researchers think we might already have evidence of something out there, small hints, strange signals that appeared once and never came back, atmospheric data that does not quite fit any known model. Let us look at some real data, starting with a cosmic threat that could explain the silence without any aliens at all. A natural disaster so powerful it could sterilize entire regions of the galaxy in seconds. Every once in a while, the universe does something so violent that it makes nuclear weapons look like sparklers. A single event that releases more energy in a few seconds than our star will produce in its entire lifetime. A burst of radiation so intense it could sterilize every planet within thousands of light years. These events are called gamma-ray bursts, and they might be one of the most overlooked answers to the Fermi Paradox. Gamma-ray bursts come in two varieties. Short bursts, lasting less than 2 seconds, are usually caused by the collision of two neutron stars. Long bursts, lasting up to several minutes, happen when a massive star collapses into a black hole and fires twin jets of energy out from its poles at nearly the speed of light. If one of those jets happens to be pointed at a living planet, the results are catastrophic. The radiation would shred the ozone layer, expose the surface to lethal doses of ultraviolet light, trigger atmospheric chemical reactions that would block out starlight for years, and potentially cause a mass extinction event. Some researchers believe a gamma-ray burst may have already hit Earth. There is evidence linking a burst to the Ordovician mass extinction event roughly 440 million years ago, which wiped out around 85% of all marine species. It happened fast. And there was no warning. Now think about that on a galactic scale. Gamma-ray bursts happen roughly once every few thousand years in a galaxy the size of the Milky Way. Over billions of years, that adds up. Entire regions of the galaxy could have been sterilized repeatedly, giving life no chance to gain a permanent foothold. The inner regions of the galaxy, where stars are packed closer together, would be especially dangerous. A burst from a nearby star could wipe out civilizations across thousands of systems simultaneously. This has led some scientists to propose a concept called the galactic habitable zone, a ring-shaped region of the Milky Way where the frequency of gamma-ray bursts is low enough to give life a fighting chance. Earth happens to sit inside that zone. Yet even here, we are not safe, just lucky. So far, gamma-ray bursts are something you cannot prepare for. There is no shield, no warning system, no defense. If one happens close enough and aimed in the right direction, every living thing on the surface would be gone before anyone knew what happened. The universe may simply be too violent for most civilizations to survive long enough to reach the stars. The Great Filter might not be social or technological. It might be a random blast of energy that resets the clock without mercy. And still, the question remains. Even if bursts erase some civilizations, surely others would survive in quieter corners of the galaxy. So why the total silence? Maybe the answer is that they are talking. We are just deaf to their language. We have been searching for alien signals, the way a person in a dark room searches for a lost key, by feeling around the only patch of floor they can reach. Radio waves, microwave frequencies, narrow bands of the electromagnetic spectrum. We assume that any intelligent species would use these tools because they are what we use. That assumption could be completely wrong. Human technology has changed dramatically in just the last 100 years. A century ago, our most advanced communication was Morse code tapped across copper wires. Now we send encrypted digital packets through fiber optic cables at the speed of light. Our own signals have become harder to detect from space with every decade that passes. Early television broadcasts leaked out into the galaxy. Modern ones barely do. An alien civilization with even a few centuries more technological development might communicate in ways we cannot imagine. Neutrino beams that pass through planets like they are not there. Gravitational wave pulses that ripple through space-time itself. Quantum-linked networks that transfer information instantaneously across any distance without broadcasting anything at all. If they are using any of these methods, our radio telescopes would pick up nothing. We would be standing in a room full of conversation and hearing only silence because we brought the wrong ears. There is also the problem of encoding. Even if we detected an alien signal, we might fail to recognize it as a signal. We tend to look for patterns that make sense to human minds, repeated sequences, mathematical constants, structured data. An alien intelligence that evolved under completely different conditions might structure information in ways that look like random noise to us. Think about how different human languages already are. Mandarin, Navajo, and Icelandic use entirely different structures and concepts, and those are all languages created by the same species on the same planet. An alien language shaped by a completely different biology, a different sensory system, a different evolutionary history, could be unrecognizable at the most fundamental level. We might have already received a message and dismissed it as interference. It might be sitting in our data archives right now, filed under static. Some researchers have started broadening the search, looking for optical signals, laser pulses, infrared anomalies, even patterns in cosmic phenomena that might indicate engineering rather than nature. Yet the search is still in its infancy compared to the scale of the problem. There is also the matter of attention. Even if an alien signal hit our receivers perfectly, someone would need to be looking at that exact data at that exact moment. Most of the sky is unmonitored at any given time. Signals come and go. If we are not watching when one arrives, it simply passes through and vanishes forever. The universe does not repeat itself on our schedule. The universe might be noisy with conversation. We might just be deaf to every single word. Yet while we struggle to hear what might already be there, a new mathematical model has emerged that makes the silence even more puzzling. It says that eventually, civilizations that want to expand will expand, and they should be obvious, which leads to one of the newest and most provocative ideas in the field. In 2021, economist Robin Hanson, the same researcher who proposed the Great Filter, introduced a new mathematical model called grabby aliens. The concept is deliberately provocative, and the math behind it is surprisingly tight. The model divides civilizations into two categories: quiet ones, who stay home and never expand, and grabby ones, who aggressively colonize space, reshaping everything they touch. The key insight is that if grabby civilizations exist at all, they would expand at a significant fraction of the speed of light and eventually fill the entire observable universe. Now, here is the twist. If grabby civilizations are common and expand fast, they would collide with each other, filling the universe with obvious boundaries and signs of engineering. We see none of that. So, either grabby civilizations are incredibly rare, or we appeared very early, one of the first. The math suggests that if we are typical, meaning we appeared at roughly the time you would expect an intelligent species to appear, then we are likely near the frontier. The grabby civilizations are out there, yet they have not reached us yet. They are expanding, yet the universe is so large and so young relative to its total lifespan that their borders have not overlapped with our little corner of space. This model makes a startling prediction. Eventually, we will see them. Their expansion will become visible as strange, coordinated changes in distant regions of space. Galaxies going dark or lighting up in unusual patterns. Yet that might not happen for millions or billions of years. The grabby aliens model has a strange consequence for humanity. If we are early, we are in a unique position. We arrived at the party before the big players showed up. That means we have a window of opportunity. If we expand now, while the galaxy is still quiet, we could become one of those grabby civilizations ourselves. Yet if we wait too long, the opportunity closes. The expanding borders of older civilizations will reach us, and our future will be determined by their rules. It is a model that turns the Fermi Paradox from a question into a timer. The silence is temporary, and when it ends, the universe will look very different. Hanson's model does not explain why the universe appears empty right now, yet it offers a framework that connects to many of the other theories. The Great Filter, the Dark Forest, the Burnout Hypothesis. They all fit inside a model where civilizations are rare, expansion is dangerous, and timing is everything. There is a deeply unsettling version of this model. If grabby civilizations exist and we are among the earliest, it means the silence around us will eventually be shattered. The first contact might come as an expanding wave of transformation sweeping across the galaxy, converting everything in its path. By the time we see it coming, our window to act might already be closed. And then there are the ideas that make us question reality itself. Proposals that say the silence might be coded into the very fabric of existence, that the emptiness we observe is a feature built into the system by design. Here is a thought that will not leave you alone once you hear it. What if the reason the universe appears empty is that it was designed that way, not by aliens, by programmers? The simulation argument, most famously articulated by philosopher Nick Bostrom, suggests that if it is possible to simulate a conscious mind inside a computer, then statistically, most conscious minds in existence are probably simulated. The reasoning is straightforward. A single advanced civilization could create billions of simulated universes, each populated with billions of conscious beings. The number of simulated minds would vastly outnumber the real ones, so the odds favor us being inside a simulation. Now apply this to the Fermi Paradox. If we are inside a simulation, the absence of aliens has a simple explanation: they were not included. The simulation was designed to model a single civilization, or a small number, and populating the rest of the universe with active alien civilizations was not necessary for whatever purpose the simulation serves. Rendering an entire galaxy full of civilizations is computationally expensive. If the simulation only needs to model one emerging species in detail, it makes sense to leave the rest of the universe as background. Static, empty, just realistic enough to seem plausible from the inside. This sounds like philosophy more than science. Yet there are testable implications. If the universe is simulated, there might be resolution limits, places where the physics breaks down or simplifies at very small scales. Some physicists have suggested that certain features of quantum mechanics, like the way particles behave differently when observed, could be consistent with a computational shortcut. Render the details only when something is looking. Nobody has proven we live in a simulation, yet nobody has disproven it either. And within the context of the Fermi Paradox, it offers a uniquely clean explanation. The silence is a feature of the system we are running on. The simulation idea also carries an emotional weight. If the universe was designed with us in mind, then our loneliness is engineered. The empty sky is a choice made by whoever built this place. We are not discovering that we are alone. We are being shown that we are alone. And the difference between those two things is enormous. Some thinkers have pointed out that if we are simulated, then the Fermi Paradox may be a clue, a signal hidden in the design. Maybe the silence itself is the message, a puzzle left by the architects, waiting for us to decode it. Whether you find this comforting or terrifying probably says more about you than about the universe. Yet, whatever the truth is, there are moments when the line between theory and evidence gets blurry. Moments when our instruments pick up something that does not fit any known model. Something that, for a brief window, made scientists wonder if they were looking at the first genuine trace of alien life. And the most recent example involves a planet roughly 120 light-years away. In 2023, the James Webb Space Telescope pointed its instruments at a planet called K2-18b, about 120 light-years from Earth. What it found set off a wave of cautious excitement that rippled through the entire scientific community. This distant world is a sub-Neptune-class planet, roughly 8.5 times the mass of Earth, orbiting in the habitable zone of a cool red dwarf star. The planet's atmosphere showed clear signs of methane and carbon dioxide, yet the detection that made headlines was a tentative signal of dimethyl sulfide. On Earth, dimethyl sulfide is produced almost exclusively by living organisms, specifically by phytoplankton in the ocean. Finding it on another planet would be extraordinary, because there is no known process without biology that produces it in significant quantities. Scientists were quick to add caveats. The dimethyl sulfide signal was faint. It needed further confirmation. The telescope was pushing the limits of its sensitivity, and there could be unknown chemical processes that mimic the signature. Yet the detection was enough to shift the conversation. For the first time, we had a real, specific, named molecule on a real, named planet that might indicate biology. A data point. Something testable, something we can go back and check with better instruments. This distant world is unlikely to be a place humans would recognize. If it has an ocean, it might be a deep water world with no solid surface. The atmosphere is thick with hydrogen. The gravity is stronger. The light from its star is dimmer and redder. Whatever lives there, if anything does, would be nothing like life on Earth. Yet that is almost the point. If life can arise in conditions so different from ours, It suggests that biology is a tendency of the universe itself. Given the right chemistry and energy, life just happens. And if that is true, the Fermi Paradox gets much harder to dismiss because it means the early terms of the Drake equation are favorable. Life starts easily, which pushes the great filter later in the timeline, closer to us. This planet has not solved anything yet it has turned a philosophical question into an empirical one. Future observations with more powerful instruments could confirm or deny the detection, and if they confirm it, everything changes. We would know, for the first time in human history, that we share this universe with something alive. There is also a broader pattern here. Over the past decade, our ability to analyze exoplanet atmospheres has gone from theoretical to practical. We are no longer guessing about what distant worlds might contain. We are measuring it. And with each new telescope, each new instrument, the resolution sharpens. If there is life out there producing telltale chemicals, the odds of us finding proof are growing with every observation cycle. And that confirmation might arrive sooner than anyone expects, because this is far from the only strange signal we have picked up. There have been others, brief, unexplained, tantalizing. One of them has been haunting scientists for almost 50 years. On August 15th, 1977, a radio telescope in Ohio picked up a signal that should not have been there. It was a narrow band burst of energy at a frequency of roughly 1420 MHz, close to the frequency naturally emitted by hydrogen, the most common element in the universe. The signal was strong. It lasted 72 seconds, and it never repeated. Astronomer Jerry Eman circled it on the printout and wrote one word in the margin. Wow. The wow signal became the most famous unexplained detection in the history of the search for extraterrestrial intelligence. It matched everything scientists had predicted an alien transmission might look like. The right frequency, the right bandwidth, the right intensity, coming from the direction of the constellation Sagittarius, with no known natural source. Decades of follow-up observations pointed every available telescope at the same patch of sky. Nothing. The signal never came back. Explanations have been proposed. A classified military satellite, a reflection off space debris, a one-time natural phenomenon. In 2017, one researcher suggested it could have been caused by a hydrogen cloud surrounding a passing comet. Yet that explanation was disputed by other scientists who found the math unconvincing. The WOW signal remains officially unexplained. It is not proof of alien life, yet it is the closest thing to a genuine anomaly that the search has ever recorded, and it is not the only one. In 2020, the Breakthrough Listen project detected a narrow band signal at 982 MHz coming from the direction of Proxima Centauri, the nearest star to our system. The signal appeared to shift in frequency in a way consistent with a source on a planet. For a brief, electrifying moment, researchers thought they might have found something real. Further analysis showed the signal was likely terrestrial interference, a piece of equipment on Earth producing a signal that mimicked an alien transmission. Disappointing, yet the fact that it took months of careful work to rule it out tells you how close it was to passing every test. There have been other close calls, fast radio bursts, repeating signals from deep space, unexplained infrared signatures around distant stars. Each one sparks a brief wave of hope, followed by a more mundane explanation. Yet the cumulative effect of these near misses is anticipation. Every false alarm refines the search. Every near miss teaches us what to look for and what to filter out. The tools are getting sharper. The sensitivity is increasing. The sky coverage is expanding. We might be one detection away from the biggest discovery in the history of our species, or we might spend another century hearing nothing. Either outcome tells us something profound, and there is one more theory worth considering before we try to pull all of this together. One that says the aliens might be out there, perfectly fine, and simply asleep, waiting for a very specific reason. This one might be the strangest idea yet, and it comes with actual physics to back it up. The aestivation hypothesis, proposed by researchers Anders Sandberg, Stuart Armstrong, and Milan Cirkovic, suggests that advanced civilizations are not dead, hiding, or trapped. They are hibernating, deliberately, because they are waiting for the universe to get colder. The reasoning comes from thermodynamics. Computation, the processing of information, becomes more efficient as the temperature of the surrounding environment drops. The cooler the background radiation of the universe, the more work you can extract from every unit of energy. Right now, the cosmic background temperature is about 2.7 degrees above absolute zero. That is cold by human standards. Yet for a civilization that thinks in terms of billions of years, it is still relatively warm. The universe is going to keep cooling. In trillions of years, the background temperature will be almost at absolute zero, and at that point, the same amount of energy could power vastly more computation than it can today. So, if you are a civilization that has already mastered everything there is to master at the physical scale, and your primary activity is computation, thinking, simulating, experiencing, then the rational move is to shut down and wait, go dormant. Store your energy, sleep through the warm ages of the universe, and wake up in the far future, when your stored energy will go orders of magnitude further. Aestivation is the biological term for a period of dormancy during hot conditions, the opposite of hibernation. These civilizations would be estivating through the current cosmic summer, waiting for the long winter when the real work can begin. From our perspective, an aestivating civilization would be invisible. No signals, no structures, no activity, just stored energy and dormant systems scattered across the galaxy, waiting for conditions that will not arrive for trillions of years. This hypothesis is fascinating because it does not require the civilization to be destroyed or to choose isolation. They are simply being efficient. They ran the numbers and decided that right now is the worst time to be awake. Every joule of energy spent today is a joule wasted compared to what it could accomplish in the deep future. It also means the universe might be packed with sleeping giants, ancient minds in cold storage, dreaming in the dark, waiting for a future we cannot even conceive of. The math behind this is surprisingly solid. Researchers calculated that a civilization could extract millions of times more computational work from the same energy by waiting until the universe cools to near absolute zero. From their perspective, running anything now would be like burning a fortune on fireworks when you could invest it and live off the returns forever. There is something almost spiritual about this image. Minds older than stars, choosing patience over action. Civilizations that decided the present moment, all of it, the galaxies, the stars, even the light, is simply not worth waking up for. And when they wake up, the universe will belong to them. We are living in the intermission of a story that stretches across timescales so vast that our entire civilization is barely a footnote. So, after 25 chapters of theories, dead ends, terrifying possibilities, and cosmic mysteries, the question remains, have we cracked the Fermi Paradox? Here is the uncomfortable truth. After 75 years of debate, thousands of scientific papers, and more than 75 proposed solutions, we still do not have a definitive answer to the Fermi Paradox. Nobody does, and anyone who claims otherwise is selling certainty they do not have. Yet we are closer than we have ever been to narrowing it down, and the picture that is emerging is both humbling and terrifying. We now know that the early terms of the Drake equation are favorable. Planets are everywhere. Rocky worlds in habitable zones are common. The ingredients for life are scattered across the galaxy. The stage is set. The universe has done everything it can to make life possible, and yet the silence persists, which means the answer lies in the terms we still cannot measure. How often does life actually start? How often does intelligence emerge? How long does a technological civilization survive? And do any of them choose to expand? Or do they all, every single one, either collapse or go quiet? The Great Filter theory suggests there is a nearly impassable barrier somewhere on the road from dead matter to a starfaring species. If the filter is behind us, then we are the lucky ones, the first, the exception. And the galaxy is ours, if we can survive long enough to claim it. If the filter is ahead, then the silence carries a verdict, and we are approaching the same wall that killed everyone who came before. The dark forest says the galaxy is full of predators, and silence is the only survival strategy. The zoo hypothesis says we are being watched and deliberately left alone. The burnout model says growth always hits a wall. The artificial intelligence filter says our own creations will replace us. The transcension model says the most advanced minds leave the physical universe behind. The astivation model says they are asleep, waiting for a colder universe. Maybe no single theory is the complete answer. Maybe the Fermi Paradox has multiple solutions operating at different scales. Some civilizations burn out, some get destroyed, some go quiet by choice. Some transcend, some never make it past their oceans. And the result, from our vantage point, is the same. Silence. Yet here is what has changed. We are no longer just theorizing, we are testing. The James Webb Space Telescope is analyzing exoplanet atmospheres for biosignatures. The search for extraterrestrial intelligence is scanning more of the sky on more frequencies than ever before. Probes are heading to the ice moons of our outer system, where oceans might hide life right in our own backyard. In the next few decades, we will either find something or we will put tighter limits on what is possible. Every observation pushes the boundaries of our ignorance a little further back. And maybe the most important thing the Fermi Paradox teaches us has nothing to do with aliens at all. It is about us, about how rare and fragile this moment might be. A species, on one small planet, just barely advanced enough to ask the question, looking up at a sky full of stars and wondering, for the first time, if anyone is looking back, the answer, when it comes, will change everything. Until then, all we can do is keep listening.